Hello, everyone. Welcome back to the AAS YouTube channel. And this one's going to be on publishing. And we're in the Author Series module. And I'm really happy today to have Stefan Portillo and Joshua Speagle with us today. This is going to be our first triplet with two authors. And you may wonder why that is, and we'll get to that shortly. But let's do some introductions from Stefan and Joshua. Joshua, why don't you tell us a little bit about where you're at and what you're doing and what you like to research.
Sure. Yeah, so I'm Joshua Speagle. I'm a fourth-year graduate student in astronomy at Harvard. So I'll be graduating in hopefully under a month and moving to Toronto. And a lot of my research focuses on the development and application of statistical methods in astronomy, sort of more on the methodological side, actually working on them, developing new techniques, and applying them to large data sets to study stars and galaxies.
Cool. Is your defense going to be virtual these days?
Yeah, it's going to be over Zoom as well.
Yeah. Okay. Interesting. Good luck with that.
Yeah, thanks.
Awesome. Stefan.
So I'm Stefan Portillo. I've been a Dirac postdoc fellow at the University of Washington for about a year and a half now. Before then, I was a graduate student at Harvard CFA, which is where Josh and I started this project. And like Josh, I also, like thinking about methodology and astrostatistics. And I guess I kind of focus on problems of photometry, which is one reason that this project came about.
Cool. Very good. All right. So now you know how or where we are and what we're doing. So let's go ahead and get into it. And this is a relatively recent paper. I will do the screen share. Screen share. And we have photometric biases in modern surveys. And what is unusual about this one is that we have, you'll notice that both Stefan and Joshua have the number 3 next to their institutional affiliations. And if you go down here to the bottom, we have equal contribution. So this is why we have our first triplet has got equal first author rights on this one. So why don't you guys go ahead and take it away and let's learn a little bit about some photometric biases.
Yeah, well, I think just to point out to anyone who might be reading this, so one of the reasons that we actually ended up writing this paper in particular was, so Stefan was working on a separate problem in photometry and had noticed essentially this bias kind of creeping in and had remembered where, that he'd seen this before and went digging around. And I got really excited about this because I thought that there could be some other ways to derive this and understand what's going on. And Stefan came back to me the next day and said, if we write a paper on this, the initials of our name will spell PSF. And after that, I'm like, oh, we have to do it. We have to publish the paper now.
Oh, very good.
That was the start of this project.
Good.
Yeah.
So Stefan deserves 100% of the credit.
That is awesome. That is very awesome. Okay, very good.
So I think since then we've already been, wondering if you want to write a paper on GPUs, then we can do FPS, or if you want to be astrophysicists, we can be SPF. The opportunities are endless.
Yeah, we had too much fun with that.
Yeah.
So I guess like Josh said, this started because I was working on a separate problem, and there's this, 4 or 5% bias that I couldn't get rid of. But then after thinking about it some more, the bias that we talk about in this paper, a statistician might kind of think of as like stats 101, and it comes from the fact that maximum likelihood estimators are always biased. Mm-hmm. But, as an astronomer, you heard that in class sometime, but sometimes it can be difficult to remember how that applies to your actual data. And we decided to write this paper because, I went to my advisor at the time, Doug Finkbeiner, the last author. He didn't think it was completely obvious. We went to some other people who also agreed it wasn't completely obvious. So we decided to write this paper. And if you go to figure 1, that really shows kind of the the main cause of the bias that this paper is about. And the idea is there's something that very important that happens if you don't know the position of a point source before you measure it. And one way to understand this is to think about a more ideal case. Let's say there's some point source and you already know its position. Maybe, Gaia measured it or something, and you know pretty much exactly where it is.
Mm-hmm. Okay.
And now you do PSF photometry on it. So this is the left-hand column.
Mm-hmm.
And, let's work in the regime where there's enough, your main source of noise is the background sky, and we're going to treat that as Gaussian.
Sure.
And in that case, the noise has an equal chance of fluctuating low or fluctuating high. And the PSF flux that you measure at the position of the source also has an equal chance of fluctuating low or fluctuating high. And what that means is, on average, you'll measure the correct flux for that point source, and you don't have a bias that you need to worry about. But that only happens because you can fix your PSF on the true position of the object, because you already know where it is. But in a lot of cases in astronomy, you're imaging new objects you didn't necessarily know it existed before, or maybe objects for which you don't have good position measurements,
Mm-hmm.
in which case you're using the same image to measure both the position and the flux. And what happens in this case is the noise still has an equal chance of fluctuating high or fluctuating low, but different things happen in the high case versus the low case.
Okay.
And so this is in the right-hand column of this figure. So if the noise fluctuates high near the true position of the object, your best fit position is going to stick around the true position. And you're going to measure a flux that's slightly high because the noise is slightly high.
Uh-huh.
But if the noise fluctuates low near the true position of the object, your best fit position might wander somewhere else to find a better fit,
Mm-hmm.
because the best fit it can come up with is kind of the fit that absorbs the most flux. So it's actually more likely to wander somewhere else where it can get a better fit and measure a slightly higher flux than you would have measured if you stayed put at the true position. And so this is a difference in behavior that happens where if the noise is high at the true position, you stick around the true position. And if the noise is low, you wander away to try to find more flux. And because of that, when the noise fluctuates low, you don't measure a flux that's as low as at the true position. You measure a flux that's slightly higher. And that actually leads to a bias, because now, instead of the cases where the noise goes high canceling out with the cases where the noise goes low, now you've got this slight bias towards fluxes that are a little too bright.
Right. Yeah. No, I like this figure. It makes nice intuitive sense. Okay.
Yeah, one of the cool things that we found, while working on this, and that we eventually investigated a lot later in the paper, is that this effect is actually really generic in photometry in almost all pipelines. And so from what we could sort of tell, we expect this bias to appear in almost all sort of modern astronomical surveys and data sets that are doing photometry this way. And so, as we'll discuss like later in the paper, it turns out that this effect is not as bad for certain sources of things you might care about, like bright stars, but it becomes worse once you allow the models to become more complicated. Because this particular effect, where you're just looking at the position, you can imagine now, what if you don't just allow the object to just kind of move around, but what if you allow it to have a different shape or a different size? Then you have many more ways that your noise can kind of be absorbed that way, and the bias actually increases.
Sure.
Right, and I guess one way that you can think about this bias is in equation 25, which is just above this figure. And there, on the left-hand side, we've got basically a chi-squared test statistic where you're, in PSF photometry, you're trying to model your image as like a PSF on top of a background and compare it to your real image. So the left-hand side is residuals squared, normalized by your noise. And so Josh dug out, this stats theorem from back in 34, Cochran's theorem. And it tells you, under certain conditions, this chi-squared like statistic for a maximum likelihood fit follows the chi-squared distribution. And that distribution has a number of degrees of freedom where you take the number of data points that you have. So we call that capital A for the area of the image in pixels, because we have kind of one number per pixel we're trying to fit. And then you have to subtract out P, the number of parameters that are in the model that you're fitting to the data. Okay. And so, this makes intuitive sense. Your degrees of freedom are the number of data points you have minus the number of free parameters that you're fitting. Basically, then we do some math and going from equation 25 then to the form of equation 29, where what's happening is these two extra degrees of freedom that you've put in, the X and Y position, or RA and DEC, if you'd rather think about that, absorb those extra degrees of freedom, allow you to move around to absorb more flux and make the residuals smaller than they should be, if you fixed the true position. And if you churn through the math, it turns out that basically every degree of freedom gives you a bias in the flux. And that bias is, if you think of it as a fractional bias, so in equation 29, we've got the bias in the flux compared to the actual maximum likelihood value of the flux as a fraction. That turns out to be the uncertainty in the flux squared over the flux squared, or in other words, 1 over signal to noise squared is a good way to think about this fraction. And so this tells you when you need to worry about this bias and when you don't really need to worry about it. So in my case, that 4 or 5% number makes sense, because I was thinking about, basically I was thinking about sources that were like barely on the detection limit, like 5 sigma. So a signal to noise of 5. So this formula tells me all of those fluxes should be biased high by 1 over 5 squared, 1 over 25, or 4%. And so for dim sources, this is a pretty substantial deal, 4%. And if you can get rid of it, which basically this formula is also a prediction. So now I know it's 4% for 5 sigma objects, so I can just subtract that out.
Right.
Whereas if your signal to noise is a lot higher, like I remember a colleague who worked on Kepler asked, okay, do I need to worry about this? And I asked him, what's your signal to noise? And he said something like, I don't know, 10,000 or 100,000. I forget the number. So, you square that and take the reciprocal, and you come to the conclusion that if you have a really high signal to noise object, this is not the first thing you should worry about.
Yep.
Right, exactly. I think a good way to look at that is actually in the, I think figure 4, is it?
Let's go look at figure 4.
Oh, sorry, no, figure 2.
Figure 2.
Yeah, so this was, we wanted to sort of showcase this a little bit. Now we had these derivations, and Steph and I wanted to do a couple of things to test this out. And so what we did was first we generated simulations of lots and lots of point sources at varying signal to noise and with varying PSF sizes. And so this is essentially the result that showcases what this bias looks like. So on the y-axis for each of these plots, you can see the flux bias as a function of the signal to noise on the left. And then the red shows this sort of basic bias we predict. And the blue actually showcases a second order correction you have to make when you get to really low signal to noise, just because the sort of first order approximation kind of breaks down a bit. The right side actually shows a fun case where this bias in the flux actually also leads to an underestimate in your errors. By just, it's a small amount, it's about half. So we just showcased that that actually holds as well, that you can actually predict both, and they both hold from lots of our simulated, checks.
Nice.
Yeah, so this allows you to sort of see, at what point you really need to worry about this. And obviously around like, signal to noise of 8 or 9, you're looking at like a 1% bias. And so this is really not any larger than I think the systematics that most people deal with when they're looking at photometric surveys.
Yeah. Cool.
And the next thing to look at might be figure 6. So we've been talking about basically a single, fitting a single image of a point source. But one, kind of cool consequence of all of this is you have to think about how you combine images across different bands or across different data sets. And people will often talk about 2 different ways to use let's say R and I band from SDSS or something.
Okay.
So you might do something called forced photometry, where you pick one of your bands, let's say R, and you find, your centroid your point source in R band, and then you take that best fit R band position and then fit your source's I band flux at that position. And so we did simulations of this sort of scenario where we call, we have a detection band, which is where you actually fit the position of the source, and the forced band where you just take the position that you found in the detection band and do forced photometry. And so the detection band acts just like our single band case. You get this flux bias because of the reasons we gave before. So that's, the detection band acts exactly the same. But the forced band, what happens is you would get, an unbiased flux if your position was actually the true position of the source. But you're actually using the best fit position from the detection band. And so you're following, whatever noise peaks happened in the detection band. And the shift might be tiny. It's probably, some small fraction of a pixel. But now there's an offset from the position you're using and the true position of the source. And you can kind of think of the overlap integral of like the true PSF versus the PSF you're using. And so you're not soaking up all of the flux that the object has in the forced band. You're missing a little bit of it because your PSF is offset. And so by coincidence, it actually turns out that you basically get exactly the opposite bias in the forced band, where you underestimate the flux in the forced band by 1 over signal to noise squared. And the signal to noise that matters is the signal to noise in the detection band.
Right.
And if you care about the color of this source, now you have to pay the toll twice. You've overestimated the detection band flux and underestimated the forced band flux. And so your color is actually wrong by 2 over signal to noise squared.
Yeah, and this effect, it turns out, really goes away if you try and actually fit all the bands together.
Yeah.
So either, and so surveys that either try and do some type of, I think it's called sort of like a stacked chi-square detection, where you kind of combine all the bands and then you detect on that stacked image. Or if you do some type of version where you try and fit a model to all the images at the same time, then what actually happens is you end up with the same behavior as before, but actually your bias spreads out across all the bands simultaneously. And so the thing that you actually care about is the combined signal to noise from all the bands. And so you get this nice effect where you get, while you do end up with the flux bias in both the brighter band and the fainter band in our sort of simulations here, the color you get is unbiased. And that sort of is really nice because that means that if you care about measuring, SEDs or things like that for these objects, you don't have to worry about this effect. And so this got us kind of scared because, a lot of surveys, including SDSS and the other ones, say that they do some version of forced photometry. And so we really were wondering, could we actually find this effect if you went to some of these, pipelines and started looking?
Okay.
And that was really interesting because in the next, I think figures 8 and 9, we actually did this where we went to a set of simulated sources in the HyperSupremeCan survey, HSC. And this is essentially what they did here. This is using SynPipe, where they essentially took their real pipeline and injected fake sources into real images. And then they ran the whole pipeline on them and then, to do a sanity check as to how things looked. And on the top panel, you can kind of see what the scatter and the magnitudes are for these objects across each of the bands. And then on the lower panels, you can see what the bias is as a function of magnitude. And the sort of red lines and the different shaded regions are trying to correct for some of these effects. We found some interesting systematics that we sort of started corresponding with the pipeline teams about that they confirmed, but we really couldn't figure out why they were there. But the key thing that we sort of found was actually that if you looked at the colors in each of these bands, we actually find this positive bias in all of them. So we found no evidence of this negative bias you'd expect from forced photometry where you underestimate the flux.
Right.
And this was super interesting to us because all of these pipelines, especially HSC, advertised they were doing some form of forced photometry. And when we dug into it, the solution to this problem was actually that the definition of force is often a little flexible. And so what actually happens is when they're doing a detection on the image, they actually allow for some small local recentering. So they allow the fit to move by just a little bit to get a better fit in the image. And that small amount of freedom actually is enough to completely decorrelate all of the bands and treat them essentially as if they're doing single band detections for most of these brighter sources.
Yeah.
So for fainter sources, essentially, you're still doing forced photometry because you're not allowed to just move anywhere. But for brighter sources, this actually means that you completely decouple the bands from each other and you're essentially doing single band photometry in all of the sources. And so that was kind of a nice resolution to this where we found essentially, we confirmed this effect actually occurs in real pipelines. And we also figured out why it sort of behaves differently than we had predicted was due to this very technical but kind of important detail about how the pipeline actually worked.
Nice. Got it.
And then, after this in the paper, so we started out with idealized simulations of just a Gaussian PSF on a background. Then we moved to injecting fake sources into a real pipeline. We also wanted to see if we could find this in real data. And so we decided to use Stripe 82 from SDSS because there you've got a bunch of short exposures covering the same area of sky, but people have also made stacks of these exposures. And this is important because to see if our prediction's right, we need to know the true flux of the source. But of course, we can't have that for real sources. But what we can do is say the stacked images from Stripe 82 are just much higher signal to noise than any of the individual images. And so for our purposes, the fluxes that you measure using the stack are pretty much the true flux, or at least they're much closer to the true flux than the fluxes that you would measure on each individual image. And so here we make scatter plots of basically the difference between the flux measured in one image, or the magnitude measured from one image and the magnitude measured on the flux versus the magnitude measured on the stack. And if you zoom in a bit, you'll see yellow and blue bands basically showing the trend of the mean magnitude bias, and the red line is our prediction. And so, of course, the bias that we identified is not the only thing going on in these pipelines, but the effect that we predicted is certainly there in this data.
Yeah, and so for us, we were sort of like simultaneously like, yay, this bias we were worrying about, we did all this work, exists in real data, that's such a nice validation. And then of course we went, oh no, this bias we predicted exists in the real data. Oh, what can we do? And I think that was, so one of the things we'd hope to do in this paper was sort of, publicize this a little bit so people could be aware of it, especially if they're trying to work at pretty high signal to noise and care a lot about sort of these small systematic effects in their photometry. So they might be able to correct for some of this on average in their data sets. But it was really nice to actually see this come out pretty cleanly in, I think, pretty much all of the SDSS bands, including the U band, even though it's substantially noisier.
Indeed it is.
Yeah, and I guess we also wanted to, publicize this because, if you're dealing with these low signal to noise sources, these sorts of technical algorithmic choices can really matter a lot, like what Josh said about what forced photometry really meant in the HSC pipeline. Another thing that we say in this paper is in figure 12, where we also wanted to make, wanted to talk about what it means to stack catalogs. And sometimes what people do is they'll take catalogs of the same area of sky and stack them by doing, some sort of source matching and then averaging the flux that you get across those catalogs and calling that, the best measurement of the flux. But if your images are low signal to noise, you've got a biased flux in each catalog, and averaging them doesn't make the bias go away. And in fact, it might mislead you because you might try to measure the standard error and you say, oh, my standard error is going down with the square root of the number of catalogs. Like, this is great. But the bias never goes away. So you're shrinking your error bars around a biased number. And so we advocate either fitting, doing your photometry on the stacked image directly, or you can still stack catalogs, but you have to subtract the bias out from each catalog before you combine them.
You do that. Yep. Okay.
Yeah, so I think one of the cool things about this project was it made us think a lot more about these particular details and how it might relate to our own work. And definitely something that showed up when we talked to people about this was I know I definitely got a lot of questions from people who went, okay, so you're saying that PSF photometry has this bias in it, but what about, why can't we just do apertures? There's less, there's no modeling involved, like you just put down a circle, like, isn't that cleaner? Should that do better? And so we sort of wanted to caution against that for two reasons. And actually we ended up making a figure to kind of look at this bias as well. So one of them was that we really, so this is figure 11, which I think is right above this. So one of the things that we, really thought was important was that in this case, we can actually characterize this bias really well from a statistical standpoint. And so when you know and understand something really well, you can take it out, and you can also model the effects and include it in other things. So just because something is biased, if you understand that bias really well, just like if you really understand a selection function, that's perfectly okay. It's just as long as you know it. The second thing is that by the same token, apertures are actually very hard to statistically characterize, just because the properties of how they actually are measured and what's going on is not nearly as amenable to lots of statistical analysis techniques. Because you're taking this continuous distribution and you're kind of putting down this aperture whose center is often determined by some type of peak counting or PSF matching algorithm. And then you're just taking this radius, which can change, the source size can change. And so now you have all these problems of, oh my goodness, how do I characterize the bias in this? How do I characterize the incompleteness? And we found that those corrections often lead to a substantial errors in the aperture photometry. So that's what's shown here. And this figure is just comparing essentially the PSF photometry versus the apertures from in Stripe 82. again, using the same sources from the deep stacks. And what you can see is that sort of the biases here in blue, sort of with these, including some other systematic corrections, essentially is, on the same order, if not larger than the biases that we found from doing our detailed derivations in the paper. So we found that aperture photometry actually, not only on average has more noise, so larger error bars, but the biases are actually just as bad. And often those are exactly because you're doing these types of aperture corrections that you're not quite sure of. And often they're much more sensitive to the background misestimation. And so you end up sort of having all these issues that sort of compound on the systematic side that mean that your biases are essentially the same, if not larger, than when you're using a PSF. So it was a really good exercise for us, and I think good for people to, so we can answer some of their questions in saying that essentially, apertures, are useful when you really don't have a good model, but otherwise they're just much harder to study, and they don't actually do much better than doing PSF photometry.
Very good. Nice. You could quantify that. Very cool.
Yeah, and I guess another common question that we got is, this is all about PSF photometry. What if I'm doing photometry on galaxies and I'm doing something like C model where I'm fitting a Sursich profile or something to the galaxy image? So if you go to figure 13, the galaxy case, has more free parameters. It's a bit harder to approach statistically, but you can still do it. And at least in a super idealized case where you imagine galaxies have Gaussian spatial profiles, which, not the most realistic profiles, but stats is easier with Gaussians. You basically find that the derivation we did earlier is pretty much correct, and you just crank up the number of free parameters that you're fitting. Mm-hmm. And so if you think of the bias for a point source as 2/2 times 1 over signal to noise squared. So the 2 on top coming from the fact that you have 2 free parameters, X and Y. For a galaxy, you're going to have at least 3 other free parameters. You're going to have some sort of measure of the semi-major axis, some measure of the ellipticity, like the ratio of the major to the minor axis, and some sort of position angle. And depending on your galaxy model, like a Sursich is going to have, more parameters, but you're going to have at least 3. And so now you've got at least 5 free parameters. Mm-hmm. And so the bias actually turns out to be 5/2 times 1 over signal to noise squared. And in, in our idealized simulated images, we show that this prediction checks out. And so it's a bit harder to correct for sources that are resolved. To do this more exactly for a non-Gaussian, you would need to either do simulations or do a lot more detailed math with the profiles. But the basic idea is still there that, all of these free parameters contribute to the flux bias.
Right. Right up front, it's a multiplier.
Exactly.
That's right.
And so we thought that this was, in particular, the extension to these resolve sources was kind of a good thing to sort of try and point out to the community, because especially as we sort of move forward with, say, like the Rubin Observatory, Euclid, and these types of things, a lot of that's going to be doing cosmology with weak lensing. A lot of that requires that you have really accurate shape measurements, but also really accurate flux measurements. So you can get good sort of photometric redshifts for lots of these sources. And so now if you're saying that on average you expect your photometry to be biased, say even at a signal to noise of 10 of like 2.5%,
yeah, that's
now a non-negligible contribution to your error budget when doing lots of those sort of very precision cosmology oriented science. Especially if sort of you imagine that you're doing some, there's some forcing going on in terms of how you're extracting photometry. So maybe your colors aren't as good as you think. But we thought that this essentially just serves as essentially a floor for what people should think their systematics are, and in some of these, because of course real galaxies are much more complicated than Gaussians, And the algorithms we're using to extract them are also more complicated. But so this is kind of like a benchmark estimate of what types of issues we should be looking at.
So does this give, well, I mean, it clearly lets you know what your bias is. Can you just correct that out once you, assuming it's a Gaussian or, you know, whatever model you want? So
yeah, we think so. So in some of the tests that we've done, essentially just applying this correction allows you to fix this. The real difficulty for some of the extended sources is what's happening if you're trying to model some very complicated profile that maybe changes between the bands, and now your bias is not quite known as well.
right.
Then you're really going to have to rely on an extensive suite of simulations and also much more detailed modeling to be able to pull that out. Definitely for stars, though, we found that this actually works pretty much, you know, as written. So right off the, you know, right off the page and into your code.
Okay. Mm-hmm. Speaking of, is there open source code for this?
There is on Josh's GitHub account. I think there's a little GitHub icon at the end of the abstract.
Yeah, so we put a little link in. So actually all the data that we used for the simulations here and from Stripe 82 and everything, that's all online. All the code used to generate the figures are also online.
There we go.
And so people can essentially, download that, play with it and make their own plots and look for, you know, slice and dice things. And you can also see, you know, the slight fudging we did to make the figures look nice. But yeah, so we wanted people to sort of be able to play with this for themselves and investigate this bias.
Very cool. Very cool. So where do you go from here? Or where do we go? Where does the community go, given what you've published here on photometric biases in modern surveys? What's the future for this? Or is it now a solved problem and move on?
Well, I think, you go ahead, Josh.
Sure, I was going to actually lead right into Stefan, which was one of the things that we found in the paper is that this bias is definitely a product of using these maximum likelihood techniques. And there's a definite reason for doing that because they're very computationally you know, straightforward to do. There's a lot of linear algebra involved, so they're great. But actually, you can eliminate pretty much all of this bias if you just are doing, rather than maximum likelihood, you're actually doing means from actual samples or some type of other estimate that's actually able to get the mean of the distribution rather than the peak. And so one of the things that Stefan's actually worked a lot on is methods to be able to do that. And that might be, you know, something to look for in the future is to have some algorithms that might actually use, say, Markov chain Monte Carlo methods or some other type of thing to get averages out. And then you can just get the, you know, average unbiased photometry directly rather than have to using this maximum likelihood method.
Yeah, and ML is quite popular.
And I guess one extension of this work that we took a first try at is this paper deals with the Gaussian noise regime, or like the sky background dominated regime. But this effect should also be really important for like X-ray telescopes and gamma ray telescopes, where the background is faint enough that you actually have to use the Poisson likelihood. And there are you know, formulas in the statistical literature where you should just be able to plug in the Poisson distribution instead of the Gaussian distribution and get a correction out. We tried to yield analytic formulas from that, or at least approximately analytic formulas. And unfortunately, the algebra gets a little messy. So worst case scenario, you know, you could, you know, just like with the galaxy case, where to get the corrections for a complicated profile, you should simulate your pipeline. At the very least, you can simulate a gamma ray telescope or an X-ray telescope. We'd really like to put a formula out, though. Like, I feel like there should be a nice formula for point sources.
You know, a closed form formula always gives one, you know, a warm fuzzy that you actually understand what's going on. So yeah, I understand the driver. Yep, cool. All right. Stefan, Josh, thank you so much for joining. And people, it's perfectly fine to contact them via their emails. We will not be saying their email here or put it in the video link below, but I will put their websites, web presences in the description below. And so thank you, everyone. Thanks, Stefan. Thank you.
Thanks for having us.
Thanks for having us.
My pleasure. All right, everyone, and we'll see you on the next author series. Thanks. Bye-bye.